Hi guys, this is Jonathan Lambert with Maths and Stats, and in this video, another video in our series of videos dealing with recurrence relations, we're going to attempt to find the closed form solution to the Fibonacci recurrence relation. And maybe just let's define the Fibonacci recurrence relation. It's a recurrence relation of the form an is equal to the nth term in the sequence is effectively equal to the sum of the previous two terms. So the nth an is equal to an minus 1 plus an minus 2. Uh, and the initial solutions are that a0 is equal to 1 and a1 is also equal to 1. So the sequence starts off as 1, 1. The next term of the sequence is the sum of the two previous, so it'll be 2, followed by 3, followed by 5, followed by 8, and so on and so forth. Now, our solution is going to rely upon the general solution for a linear homogeneous recurrence relation of degree 2, which this is. And let's recall the general solution, okay, of a linear recurrence. So let's say our recurrence is of the form an is equal to a times an minus 1 plus b times an minus 2, where we're given initial solutions. So where we have a0 is equal to some value, let's say v1, and a1 is also equal to some other value, let's say v2. So we have a linear recurrence. It's of degree 2 because the nth term is defined in terms of the previous two. It's homogeneous. Each term is raised to the same power, in this case 1, also making it linear. And we have constant coefficients of the preceding terms to the nth term, a and b. And what we know is that the general solution the general solution, right, is basically that the nth term is equal to some number c times r1 raised to the power of n plus some other number d times r2 raised to the power of n, where r1 and r2 are solutions, okay, to the characteristic polynomial. The characteristic polynomial, okay? And the characteristic polynomial for a degree 2 homogeneous system or recurrence is r squared minus a is the coefficient of the preceding term to the nth term, okay, times r, minus b, which is the coefficient of the second term that precedes the nth term, which is equal to 0. So R1 are basically solutions to this system. In the Fibonacci case, the coefficient of the nth minus 1 term and the nth minus 2 terms are both equal to 1. Okay, so this basically in this situation will be r squared minus r minus 1 equals 0. So once we find r1 and r2, the general solution is two constants times those values. Okay, we have to find the constants c and d. Okay, so where c and d, okay, are determined okay, based on the initial solutions to the system. So initial solutions, okay, to the system. So based on the values of a0 and a1 in this case. Okay. So if we were to proceed now to solve this, so the solution now to this particular recurrence of Fibonacci, let's say our solution. Okay. Our solution is going to need to focus on the characteristic polynomial. So the characteristic polynomial, right? Because we need to find the R1 and the R2. Okay? The characteristic polynomial for this particular recurrence, you see that this is once times a of n minus 1 and this is once times a of n minus 2. So the characteristic polynomial is going to be r squared minus r minus 1 equals 0. Now, we won't be able to solve this using the rational root test, and we'll actually have to use the quadratic formula. Okay, so recall the quadratic formula says that the solutions to a quadratic of the form, let's say ax, so the solutions of a quadratic of the form ax squared plus bx plus c, okay? Solutions equals 0. The solutions are that x is equal to minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. Right? So you can see that our A term is the coefficient of the R squared is 1, our B term is -1, the coefficient of the R, and our constant term is also -1. So our solutions, okay, so therefore we have that R must be equal to minus times the B value, so it's minus times -1 gives us 1, plus or minus the square root of B squared, once again, minus times minus is positive, that gives us a 1, minus 4 times A, which is minus 4 times 1 is -4, times C, which is -1, gives us a -4. Sorry, gives us a positive 4 now. So we have 1 plus 4 gives us root 5 all over 2 times A is 2. So our solutions are, or 1 is equal to 1 plus root 5 over 2, and or 2 is equal to 1 minus root 5 over 2. So we've now found our 1 and our 2. Okay? We have to rely upon the quadratic. We have to rely upon the quadratic formula to solve a quadratic. Okay? And you can see that we've got it in relation to this. They don't look nice, okay, but it's okay. We just deal with them. So now what we need to do is we need to find, so our general solution so far, let's actually maybe say that, right? So our general solution so far is